Let's go over this. And remember, these examples do not have pictures. I wish I would give you a bit more with pictures, and you will see more as you move along. Okay. All right. So chef sets an oven timer that displays 1 minute increments to 55 minutes. You're focusing on the increments, right, or the markings, right? That's where you get your precision from. So it's 1 minute. This precision is the limitation of that device, and this is telling you that you can only get it to the nearest minute, right? Uncertainty is half of that, so it'd be half a minute. You could write down 30 seconds. It's okay, but I will just leave it like that. A school nurse measures a student's temperature to 37.8 degrees Celsius. You don't have any idea what the increments are, so you got to go by this number that you're given, right? So this would be words, right? It's kind of telling you here, this is just a number, right? So I told you this image, words, and the actual value. So we are assuming that the precision of this device is to the nearest 0.1 degrees Celsius, right? Because this could go up by 1 or down on the 10th here. Uncertainty is half of that, right? We just split that in half, so you get that. A jeweler weighs 1.243 grams of gold. The precision in this particular case, we're down to the third decimal, so it's 0.001. So make sure that on the third place you put a 1 and it's grams. Always have units attached to it. Okay, it's a little blurry, is it? Or is it just me? There you go. And so dividing that by half, or by 2, no, this, sorry, 0.0005 grams. So the uncertainty, the more precise it is, the smaller the uncertainty. Does that make sense? The more precise you are, uncertainty is kind of like the unknown, like you could be off by that. The more precise you are, the smaller your uncertainty gets, right? Which is good, right? A survey technician records the distance between two fence posts to be 1,200 meters. So we're assuming this thing can only get you as close to the meter. That's it. There are no decimals here. So that'd be 0.5 meters as your uncertainty. Okay, so I hope that makes sense. Right, maybe I will highlight the 3 here. That's where we got that from. We highlight that last one. That's where we get the whole meter to the nearest meter. Write this down next to it, because sometimes it will say this device is accurate to the nearest meter. It's like, wait a minute, those are markings. That's like as close as that device can get you to the actual measurement. Okay, now word problem. A track and field meet. At the track and field meet, the gold medalist won the 100-meter sprint with a time of 10.23 seconds. What is the precision of the timer used? So the 100 meters is kind of there to throw you off. We're looking at the time, right? So the precision is 0. Don't look at the number, the decimals. There's 2 decimals there. So that's the precision of the timer. We're assuming that. We are assuming, I give you that. We are assuming, we don't know for sure. What was the uncertainty of the timer used? To split that in half, I'm actually going to show that. Write the sprinter's time, including the uncertainty. So this is measurement. That's what they're asking for. Measurement plus or minus the uncertainty. That's how they want you to write it. Because remember, you could be over or under by the uncertainty. So you go 10.23 seconds plus or minus 0.005 seconds. See, this is never done, never really done in real life. But when you hear a poll on the radio, that actual report has a plus or minus. 85% of Canadians, spend 3 hours a day on their phones. They don't tell you plus or minus. Like, it's just not cool to say that on the radio. Like, they don't bother with it, but the actual report always has an uncertainty there. Okay, if it's done like professionally. Given the uncertainty, write the maximum and minimum times that could have been taken during this race. So first of all, we started off with our actual time, and then we said, hey, this precision of this measurement device is this, which means you can be off by this much, which means that this time can be slightly over or slightly under, but that timer that you were using cannot give you that, right? So let's go max here. The max, you just take the 10.23 and you just add the uncertainty to it. Never round here, okay? And the min is 10.23 seconds minus 0.005 seconds. Okay? And so when you add these together, use your calculator for this. I don't want you to just ballpark it and then get it wrong. It'll be too bad to get it wrong. Okay? So basically, if you add this, you get 10.235 seconds, right? Because you're adding 23 plus 0.005, so that 5 is on that end there. And this is 10.225 seconds. I will ask you one more time. Is this starting to make a little bit of sense? Just a little bit, a tiny wee little bit? I'm trying my best here, guys. Like, this is all I have. Like, I don't have like computers or cool videos or whatever to show you. This is what it is, right? But I'm talking about it the whole time. Every time you take a measurement, that device has a precision to it. It could be a very precise device. It could be a device that isn't very precise. But if we find out the precision, we know the uncertainty is half of the precision. And so then we find out, hey, you could actually be over or under by a little bit. We kind of ignore it in real life, but this is a fact, right? All right. Now I need you to go back to your booklets for a bit, because the second page you cannot do yet, the page 15. So I'm going to get you to go to page 87 in your booklets. And so today we're learning something new when it comes to adding and subtracting numbers that have an uncertainty attached to them. I put that heading in there, and I would like you to like highlight and make sure you see that when you flip through your booklet, that this should stand out, because you're going to get quite a few questions like this. Okay. And so basically, when adding or subtracting measurements, each of them has their own uncertainty. So the combined value will also have an uncertainty. So I always go back to like a Canada Post office. Have you ever sent a package? Have you ever dropped off a package or made an Amazon return? What do? They put it on a scale, right? And they record the weight. So that every single package is being recorded, and eventually it probably goes on a plane, right? So they have like this big cargo, right? It goes on a plane. They need to know how many packages are on there and what's the combined weight. Well, every time you weigh something, there's a bit of an uncertainty that follows that package. And when you weigh another package, there's an uncertainty which gets added to that pile, right? So every time you measure something and you add it, there's uncertainty that gets combined, that gets added up. And that's what we're going to talk about today. The uncertainty of the final amount, here it is. The uncertainty of the final amount is the sum of the measured uncertainties. And this is what we call it, combined uncertainty. Write this down. There's a combined uncertainty. So if they ever talk about, hey, find the combined uncertainty, they want the uncertainty of all of these things combined. Packages, you'll see the different scenarios that we have. Another one is if you grab a bucket and you fill a bigger container, every time you scoop out with that small bucket and put it in the container, there's a little bit of uncertainty that follows you. Do you think about that when you do that? No, we never do. We never think about that, but that's actually happening, right? So we need to be very aware of that. Okay. I will add this note here for you. Weighing all items at once will have a lower combined uncertainty. As opposed to weighing them individually. So if you have a choice to measure all packages at once, stack them all on this big scale, as opposed to weighing every package individually, you will be off if you'll be off by more if you do them individually. Oh, that's guaranteed. And now let's do some math. So in case you can't read that because it's a bit cramped in there, weighing all items at once will have a lower combined uncertainty as opposed to weighing them individually. Okay. So when you board a plane, we haven't boarded planes in a while, maybe most of us, they ask you for your weight, right, as you board the plane. So they individually add up the weights, right? If they could put us all on a platform and just weigh us all at once, we would have a better, less of an uncertainty as to what the actual weight on the plane is. Right? And then it gets me to this: we all lie about our weight. So why would they rely on what we say, right, to get on the plane? I don't know. I hope they make up for that somehow. Maybe they have a board where you're standing out and the person on the other side can actually tell what your actual weight is. I don't know. They do something. All right. Example 6. Marcy is a carpenter. She's installing sheets of plywood as subflooring on a balcony. So using plywood to put it down on the floor, right? She has measured 2 of the sheets to be 2.25 by 130 meters long using a tape measure marked in centimeters. I don't like this example, the way it is. So we're just gonna do this. Can you follow me? We're gonna get rid of this part. It just makes it too complicated. I just want you to be able to look at those measurements and just be able to do it based on that. So get rid of using a tape measure marked in centimeters. Just get rid of it. Okay. This is all we've got. Write the lengths of each sheet of plywood in the form measured value plus the uncertainty. And we are going to do that. Watch here. That's why I left room here. We're gonna do A right here. And just draw your plywood sheet like this. Right? We know that this is 2.25 meters and this is 1.30 meters. Okay. Would you agree that they both have the same precision? Both measurements have the exact same precision. Can we agree on that? Yeah, they both have 2 decimals, so that's good. So let's go over here and just say precision for both of them will be 0.01 meter. And therefore the uncertainty is 0. Don't guess. Use your calculator to divide it by 2 if you're not sure. Of 0.005 meters. So this is what we're focusing on. So we're going to state our length is 2.25 meters plus or minus 0.005 of a meter. And our width is 130 meters plus or minus 0.005 meters. So we've just done that. That's what they wanted us to do. Okay, so let's cut this here. B is asking, what is the total length? Total length including uncertainty. So you gotta hone in on that. Of 2 sheets if they were placed end to end. So let's draw that out here. So one piece of plywood and another piece of plywood, and they measure the same, right? So let's call this ply 1 and this is ply 2. We know that this is 2.25 plus or minus 0.005. And this is 2.25 plus or minus 0.005. Both of these sheets have their uncertainty that follows them. Yeah. Oh, sorry. Oh. I think you are right. Yes. 2 sheets to be this and this. How can we fix this? It's easy fix. Thank you for pointing that out. You are right. Did you get what just happened here? It's telling you like that both plywoods have different lengths. And I just completely butchered that. I saw it as length and width. So what we're going to do is 2 sheets to be 225 by, so cancel this, 225 by 130, and we're going to get rid of that long. Can we do that? Oops. I like to be schooled by my students. That's quite awesome. So sorry about that. So 2 sheets, and we're just going to say that they both are 225 by 130. So the 130 is just for decoration purposes, but we're focusing on the length here. So plywood 1 is this, plywood 2 is this, okay? So we want to know the combined length, like total length of this. We want that. That's the question mark here. And so the way I'm going to show you to do this is 2.25 plus or minus 0.005. And it's implied that you're going to have to add here, right? You're going to have to add both of the lengths and their uncertainties like that. You have to put the uncertainties, they come with them. If I hadn't butchered this would have been 225 and this would have been 130, right? But they both would have had the same uncertainty. So now we go line, add this up. What would this be? 225 and 225 is 450. And now I'm going to add my units again. I kind of dropped them for a bit. Plus or minus, let's add these up. What do you get? You should, if you're not sure, use your calculator, okay? 0.01 of a meter. And so this is what they were after. If I hadn't made that mistake, this wouldn't have been 450 because we would have added 225 and 130. But this part is still the same. This is the combined uncertainty. So now that's the total length and its uncertainty next to it. And if you added a third sheet, you would keep doing that. You keep on adding the uncertainties as you move along. Okay? We're good? So this sheet, this total length could have a max length and a min length, right? It could have a maximum and a minimum possible, right? Let's do another one. I honestly think I'm just going to do these two and then I'm going to let you work because this is basically the same over and over. Okay, so let's read this. Junior has a bucket of water with 20.5 liters in it. He needs to draw some water for some plants using a smaller jug, which can hold 1.2 liters. So let's highlight our numbers here. If Junior draws 3 jugs from the bucket, determine how much water will be left in the bucket, including the uncertainty. So what I'm going to ask you to do here is 20.5 liters. Let's get its precision and the uncertainty because we need to figure out the uncertainty. They didn't give it to us, right? So we know that it's 0.1 of a liter and the uncertainty would be half of that, which is 0.5 of a liter. Now I can conclude from this, right? I have everything I need to state this, the bucket with its uncertainty. And then I'm going to do the same with this smaller bucket, which is 1.2 liters. The precision is also 0.1 liter. It could have different precision and different uncertainties, so just watch out for that. Uncertainty is half of that, which happens to be the same as the original bucket. So I kind of do my prep work ahead of time. And this is where you can do it in different ways. I will show you the long way, perhaps. Plus or minus its uncertainty. So let's start with the big bucket, right? The big bucket, and we're drawing. So when you're drawing water, I'm assuming you understand that it's minus 1.2 liters plus or minus 0.05 liters. That's one small bucket. Another small bucket. Oops. And the third bucket. So you're drawing 3 buckets, and each time you have to repeat that, right? And you go like this, and this is where it gets a little tricky. Let's do the part that we all know how to do, right? So 20.5 minus 1.2 minus 1.2 minus 1.2. This might be too tedious. If you're making 10 buckets, you would probably just go times 10, right? And so you're left with this 16.9 liters plus or minus. Here it gets tricky. Your instinct would be to subtract, right? but you don't. You keep on adding the uncertainties regardless of what happens here, right? So we always add uncertainties. You need to add them, and they're all the same. So watch what I'm going to do here. I'm just going to go 0.05, like the first one, times 4, because I'm combining 4 uncertainties that are exactly the same, and that gives me 0.2. This is how much water would be left, plus or minus 0.2 liters. It doesn't ask us, but I'm going to do it anyways. From here, we can get the max, and we can get our min. What's the most you can have in the bucket? What's the least amount you can have in the bucket? That's what this is saying. 16.9 plus 0.2, 16.9 minus 0.2. This is 16.7 liters. No, sorry. I reversed it. Adding, right? So 17.1 liters. And this is 16.7 liters. You could have as much as 17.1 liters left or 16.7 liters left. I did that because for B you needed to know that. If junior needs, and this question isn't specific enough, if junior now needs 17.5 liters, that's what it's supposed to say, for a tree. So if you need this much left for a tree, will you have enough water? And so the maximum you could have is 17.1, so you don't have enough regardless of what happens here. He will not have enough, comma, since the most that could be left is 17.1 liters. Okay. And some of these questions may or may not go through all these steps. You just have to read carefully. And let me just assign, maybe I'll just leave it down here because some of you are copying. Page 15 in the workbook. Not in here, but in the workbook. Work on that for a bit, and then I will reassess from there. Okay? If you're done that page 15, go to page 89 and work on questions 3 to 6. Wait a minute, just double checking. Yeah, 3 to 6. Some of you will be done, that's why I give you that to work on as well.